Hello everyone, this is Swati from Aeronautical Engineering. Today we are here for the seminar topic called Hypersonic Missiles Challenges. To hypersonic missiles. Hypersonic missiles are advanced weapons that travel at speed greater than the Mach 5 or 5 times at the speed of sound. That speed makes them incredibly fast and difficult to track or intercept. Unlike traditional ballistic missiles, hypersonic missiles can maneuver mid-flight, make them even harder to defend against, while their potential in defense and strategic welfare is massive. That development and deployment of such missiles several uh, faces several technical and engineering challenges. These challenges are particularly critical in the field of aerospace propulsion, where extreme heat, pressure, and structural stresses must be carefully managed to ensure success. Extreme thermal, extreme thermal heat and thermal protection. One of the biggest challenges in hypersonic missile techniques, managing the extreme heat generated during flight at hypersonic speed. Frictions with an atmospheric creates temperature exceeds 3000 degree on a missile surface. Traditional materials cannot withstand the heat for long duration. Therefore, advanced thermal protection systems such as ablative coating and ceramic composites are required. Design these systems is complex because they must be lightweight, durable, and capable withstanding thermal cycling. Even small imperfections can lead to catastrophic failure. Thus, uh, developing robust DPS is a major area of research in hypersonic propulsion system. Propulsion system limitations. Propelling a missile at hypersonic speed requires high advanced propulsion systems like scramjet, supersonic combustion ramjet. Unlike traditional engines, scramjet do not carry oxidizers and instead rely on atmospheric oxygen, which makes them more efficient at high speed. However, scramjets only operate if effectively with a narrow speed range, typically more above Mach 5, and require initial acceleration from the system. Design engines that can smoothly transition from subsonic to hypersonic remains a very challenging. Engineers must optimize fuel injection combustion stability, airflow control inside the engine while maintaining structural integrity under extreme thermal pressure. Structural integrity and materials. Hypersonic missiles experiences intense aerodynamic forces and heat vibration that can damage their structural integrity. Traditional aerospace materials like aluminum alloy are not strong or heat resistance enough for this condition. Advanced materials such as titanium alloy, carbon, carbon composite, and temperatures. Ceramics are being explored. However, these materials are expensive, hard to manufacture, and somehow brittle. Balancing strength, weight, and heat resistance is a complex task. Engineers must also consider fatigue and thermal compression expansion, which can cause structural failure, is not properly managed. Ensuring the missile remains intact throughout flight is a key engineering challenges. Aerodynamic stability and control. Maintaining stability and control at hypersonic speed is extremely difficult due to shockwaves, turbulent airflow, and rapid atmospheric changes. Hypersonic vehicles are more sensitive to small aerodynamics disturbance, which can lead to instability or failure. Control surfaces such as spine or canards may not work efficiently at high attributes and speeds. Engineers must design specially guided systems that can respond rapidly to changes in flight conditions. Computational fluid dynamics simulation helps in predicting airflow behavior, but real world testing is still essential. Achieving reliable control is essential for accurate targeting, and safe operation. Navigation and guidance issue. Navigation and guidance is a critical for hypersonic missiles to reach their target accurately. At hypersonic speeds, GPS signals may be destroyed or delayed, and onboard sensors may experience difficulties due to intense heat and vibrations. Moreover, traditional guidance algorithms may not work effectively due to rapid change in position and speed. Engineers must design robust initial navigation systems that can work independently of external signals. Integrating artificial intelligence and machine learning into guidance systems is also being explored and to enable real-time decision making and adaptive targeting under extreme conditions. Air breathing versus boost glide system. Hypersonic missiles generally fall into two categories: air breathing and boost glide systems. Air breathing missiles such as scramjet powered vehicles drawn in atmospheric air for combustion. Boost guide systems are launched using rockets and they glide through the atmosphere at hypersonic speed. Each has its own set of challenges. Air breathing system requires advanced propulsion and airflow control, while boosting glide vehicles need precise launching angles and returnary control. Designing effective, reliable systems for both categories requires a deep understanding of propulsion aerodynamics and material science. Engineers must also decide which system best suits the missile professional profile and operational requirements. Testing and simulation difficulties. Testing hypersonic missiles is very expensive and risky. Building test ranges and facilities that can simulate hypersonic condition is a major hurdle. Ground testing using wind tunnels or shock turbines can also approximately certain aspects of hypersonic flight. Full-scale flight testing is often the only way to validate results, but it involves significant cost, safety risk, and limited repeatedly. Computational simulation helps, but modeling hypersonic flow accurately is very challenging. Even small error in simulation can lead to incorrect conclusion. Therefore, creating a realistic testing environment in a bottleneck in hypersonic missile development. Communication blackout during flight. At hypersonic speed, a layer of ionized gas called plasma forms around the missile due to intense heat. This plasma can block radio signals, causing a temporary communication blackout. This makes it hard to control or track the missile during certain phases of flight. Solutions include using alternative frequencies, high gain atoms, or even operational optical communication methods, but each has its own limitations. Overcoming this blackout is really crucial for real-time guidance, tracking, and safety monitoring. Research continues into developing robust communication system can be withstand or bypass plasma interface. Uh, so next, play-dot integration. Fitting all necessary systems, guidance, propulsion control sensors into a compact missile name is a huge engineering challenge. Hypersonic missile must be lightweight or reach high speed, but also strong enough to carry payloads. Designers must miniaturize electronics, use compact fuel systems, and optimize every component to save space and weight. Integrating different subsystems without interfacing is also difficult for intense heat from the engine should not affect the navigation system. This requires careful thermal isolation and component placement. Balancing speed, payloads, and system integration is one of the toughest part of hypersonic missile design. Environmental and atmospheric effect. The missile performances can affected by the Earth atmosphere, especially at a verifying altitude at a high speed. Small changes in air density or temperature can cause big difference in drag lift or heat generation. Weather conditions like strong winds or turbulence can also impact accuracy and stability. Additionally, as the missile re-enters lower layer of the atmosphere, it may experience volatile heat and pressure spikes. Engineers must design the missile to handle the wide range of environmental conditions, making atmospheric modeling an important part of hypersonic missiles development and testing. Cost and management challenges. Developing and producing hypersonic missiles is highly expensive due to needs of specialized materials, precise manufacturing techniques, and rigorous testing. Components must be built on with an extreme conditions, which arises materials and labor costs. Advanced machining, additive manufacturing, and nanotechnology can be explored to reduce the expenses. Still, mass producing these systems remains challenging. Moreover, testing failures are costly and setback development timelines. Cost-effective manufacturing techniques are essential for making hypersonic weapons variable for military use and a large scale without compromising on safety performances. International competition and security risk. The risk of deploy hypersonic missiles techniques has a lead to growing global competing countries like the United States, China, Russia heavily investing the field that raise rises concern about national security, arms control, and risk proliferation. Hypersonic weapons are difficult to defend against and could lead a strategic instability. Therefore, alongside technical challenges, there are geopolitical and ethical concerns. Engineers and policymakers must work together to ensure the techniques and develop and used responsibility, avoiding escalation and maintaining global peace and stability. Integration with defense system. Deploying hypersonic missiles requires integration with extensive military and defense system. This includes launch performances, targeting systems, communication networks, and early warning radars. Hypersonic missiles travel so fast that current radar and tracking systems may struggle to detect and respond in time. This creates all needs new tracking technologies and advanced sensor fusion. Moreover, command and control system must be upgraded to handle real-time data and fast decision making. Effective navigation ensures that hypersonic weapons can be used strategically and safely in defense operation without causing consequences. Conclusion for future work. Hypersonic missiles promises revolutionary capabilities in defense and aerospace, but they come with some significant technical and economical ethical challenges. Future work will focus on developing better propulsion system, more heat resistance material, improved testing methods, and advanced navigation techniques. Integrating the AI and machine learning could help manages complex systems and enable smarter control in real time. International cooperation and regulations may also be necessary to ensure responsible use. Ultimately, solving these challenges will determine how safely the effectively hypersonic missiles are adopted in future aerospace and defense applications. Thank you.